star sum of a graph. So for this problem, we need to understand what is a star graph. So this is like a star graph. So we can find one node, and it is connected by some edges. So for this graph, we can find a node it is connected with some edges, and this is going to be a star graph. And we also have these examples. Maybe we also have some other examples. Maybe, yeah, this is also a star graph. It connected with only one edge, or maybe it connected with two edges. This is also a star graph. So what we are going to solve is that we're going to return the maximum star sum of a graph containing at most k edges. So for example, if we are calculating containing at most 4 edges, it's going to be something like this. And for this node, it's going to have a node. For example, it can be 0. This is 1, 2, 3, 4. And for each of the node, it have a value. Yeah, so for example, this is node 0, it has a value of 1, and this is node 1 has a value of 2. Yeah, we just need to check the maximum star sum of the star graph. Yeah. So as we are giving a graph, we can turn the edges into an adjacency list, and we're gonna use this adjacency list to solve the problem, because for each of the star graph, it's gonna have at most 2 edges. It's going to be something like this. So for example, this is our node 3. It's connected with node 1 and node 4. And we just need to check the value. So for this node 1, it has a value of 2, and for this node 4, it has a value of 10. So 2 plus 10 and plus the node itself. For this node 3, it has a value of 4. So it's going to be 16. This is going to be our final answer. I think let's just solve it directly. We just need to understand what is the meaning of at most k edges. So the edges can be 0 or can be 1, but at most k edges. Yeah. So as I said before, let's just define an adjacency list, and for UV inside the edges. So for GU, we're gonna append a value. But for this graph, definitely we don't need to traverse the graph because it is just a star graph. We just need to put the values inside. So it's going to be values of V. And similarly, for this V, we just need to append the values of U. So for this adjacency list, we're going to have a K. K is the node, and the value is just the values of all the adjacent node. So for example, for this node 3, yeah, it has 2 values instead of 2 nodes. It is the adjacency node. It has the values of 2 and 10. We just need to sum up together 2 plus 10 plus the 4. Yeah. Now we just need to loop through the graph. So let's set the result to be negative infinity, as we are going to check the maximum value. So for let's say for any node, let's set n is the node, and the value gonna be an array. So for NA in g.items, yeah, so A is an array of all the values of the adjacent node. So first of all, we just need to sort the A as let me set it reverse to true, because we're gonna calculate the maximum value. So the result is gonna be the maximum of the result. As we can choose at most k elements from the array A. Yeah, so let's just use the sum. It's gonna be array A with k elements. So finally, we need to set the result. It's gonna be the maximum result with the maximum of the values. Because we can choose at most k elements, so this means we can also choose k equal to 0. We can choose no edges. It's gonna be the node itself. We just need to check the maximum of the values of all those nodes. But if we can choose edge, maybe we're gonna have a bigger value. So this is why we're gonna use a result with the maximum of the values. Finally, we're gonna return the result. But currently, there is a problem. The problem is about this sum of A with k elements. So this is wrong, because inside it can be negative values. What if it has negative values? It's gonna make the result smaller and smaller. So definitely this is not what we are doing. So for example, let's just use an example. Maybe we have a node of 3, we have some values, and maybe this k is equal to 2. Yeah, so k equal to 2, we have some values. Maybe we have a 15, and we have a negative 9, and we have a negative maybe 18, because this is array A, it is sorted in decreasing order. Yeah, so if k equal to 2, that means we're going to choose 2 values. Definitely this is not okay. We must choose 1 value, because we're going to choose the maximum value. Yeah, so this means inside here, we need to check if the value is more than 0, we're going to sum up the value. Otherwise, we don't need. So for this example, the sum of the result is going to be 15. Instead of 15 minus 9, it's going to be 6. So the result is going to be 15. How can we get that? So we need to change a little bit. So for here, let's say we're going to use x. So for x inside the array a to k, if this x is more than 0. Yeah, if it is more than 0, definitely we're going to sum it up. Otherwise, we don't need it. So this is something like the greedy idea. Yeah, but it should not be so difficult. Now let me just run it to check. Oh, it didn't work. Let me think about it. Yeah, it didn't work because I forget to sum up the value of the node itself. Because currently for this node I only plus all the edges, but I didn't consider the node itself. I have to include the node. So the node is going to be values of this node. It's going to be values n. Yeah. Now let me just run it. Now as you can see it works, and it passes for all testing cases. And let me just submit it to check. Yeah, as you can see it passes for all testing cases and it's pretty fast. Now let's analyze a little bit about the time complexity. This is a graph. So from here, the time complexity is going to be E plus V. E is the number of edges and V is the number of vertices from here. So let's just check. So this is the number of nodes and the number of vertices, because it is something I think like a tree structure. No, I don't know, but it doesn't matter, because the number of the edges gonna be minimum of n times n minus 1 divided by 2 to 10 to the power 5. So this means the number of edges is also 10 to the power 5. So from here, the time complexity is 10 to the power 5. And definitely it is E plus V. And from here, we just loop through the graph, and for each value of the array, we just made a sort. So for the sort, it is n log n, and how many nodes inside the items, maybe it is also n. So the time complexity is let me just think about it. For here, we just check each of the items, and for each of the items we're gonna sort it. So for here, the time complexity is n log n. It is not n squared log n, definitely. Yeah, because let's just imagine we just have only one array, so this means it runs for one time of a dot sort, so it is n log n. If there's some sub-arrays, it must be very small, and the sum up of all the sub-arrays is going to be 10 to the power 5. So for each of them, it is this array, maybe m times log m plus others, and all those values are going to be less than and equal to n log n. So the time complexity gonna be n log n. So that is why it can pass for all testing cases. I think that's all about it. Thanks for watching. See you next time.